Welcome. We will explore how to think about the music with trigonometry and how to think about the geometry of the music. Normally, we here start with the instruments first with the patch numbers. Before going into the patch numbers and instruments, we are trying to explore here the nature of the architecture with which we will design these. For any song or for any musical piece, we manage the music with tracks. We can have n number of tracks, but the track number 0 and track number 1 for the MIDI specification are used for the lyrics or all other kind of metadata, for the copyright kind of things, or for the tempo storages, or for other kind of meta informations for the music playing, like the kinds of instrument specific systems, or the way we want to channelize the music, or if we want to handle the different kind of controllers, then we try to manage those things in track number 0 or track number 1. Track number 2 onwards are for the musical data, which are not meta events, which are the musical events. Channel number 9 and channel number 10 are specifically for the percussion instruments, and even if we put the non-percussion instruments in channel 9 and channel 10, then they behave like the percussion instruments. So better we should take the non-percussion instruments in channel number, other kind of channel numbers other than 9 and 10. Every patch number specifies some kind of instrument. So before putting any note, we have to assign the patch number, that is the instrument on which we want to play the note. Every note has a duration. We have taken the duration here in the milliseconds and microseconds way, such that we can define for what millisecond to which millisecond we want to play which kind of note. We have taken here the things as 1,000, that is taken as 1,000 gap. We could take it as 300 or 200 milliseconds, but we have taken it 1,000 to demonstrate how long a note will delay in when it is played. One more thing we want to show here is the note numbers and their frequencies. We have listed here total 128 number of note numbers, and their names are also described here. You can pause the video to slowly study the frequencies corresponding to the note numbers here and the name of the note numbers. When we are writing this with the slash, that means both are having the same frequency. Suppose 58.27 Hertz is for A1 sharp and B bass 1, both have the same frequency, and that is the 58.27, that is the frequency. In this way, when we proceed towards the last achievable frequency in the synthesizer, that is 13289.75 Hertz, and this has the note number G9 sharp or AB bass, A bass 9, that is the 9th octave, and 128 is the 9th octave. And 9th octave starts from the note number 120, which has the frequency 8372.02. Different kind of instruments cannot render every kind of frequency properly, nor if we choose the wrong channel number like channel number 9 or channel number 10, the behavior of the instruments rendering changes. So here we have explained the note numbers which are having some frequencies, and as per music theory, the note numbers have some music theory names. Those are like A0, A sharp 0, BB 0. But we sound engineers or the mathematical engineers, who design the circuits for these synthesizers, or whoever who design the mathematics for the music rendering, they hardly bother these music theory names, we bother with the note number and the frequencies. We understand frequencies only, and we understand the delays. We don't understand this kind of A0, A sharp 0, B0. We cannot understand these kind of things. More point here is the instrument numbers are the patch numbers. Patch number 1 means it is the acoustic grand piano. Patch number 2 means it is the bright acoustic piano as per the MIDI specification. Patch number 3 means it is the electric grand piano. In this way, in this video, I am showing you the explanation of how our patch numbers are demonstrated here. I am showing it slowly so that you can note it down, or you can pause the video to check the names here. I want to make this series such that you can listen how the notes in different instruments are played and how it renders, how it looks like in our ear when we listen the different patch numbers with different kind of instruments. And here I can show you a demonstration that these are the patch numbers, and suppose I am trying to show you how the patch number 105 will look like when we will render it with our geometrifying trigonometry tool. How will it look like? Suppose I want to export it with the patch number 105, and in the input sheet, if here I type it demo, then it will take the name patch demo 105, and if we click this button, then it will save the file at the location here. At the location here where I have kept this Excel file, I have written a whole macro for this so that we can save it here. And after this file is saved, suppose after this file is saved here, it is saved with a kind of notepad like data, where track number, channel number, patch number, and then the frequencies of the start and end are given, and the duration 1000 to 1000, 1000 to 2000. In this way, every of the notes are played for the 1000 milliseconds, that is the 1 second, and the frequencies are written here for every note numbers. And in the lyrics part, I have already taken it to the note numbers or note descriptions are taken as a lyrics, so that we can get the CAD file where we can see the geometry of this whole music. The 128 notes are played. All of these 128 notes are played 1 second each. So 128 millisecond I have to assign for this data, and let's say I am renaming this to smaller name so that we can get the file here. Now we will run this tool. There is a geometrifying trigonometry tool, and with that we can generate this music. Say here we can configure our music like this: 128,000, that is 128 second with the 120 beats per minute. I am taking 1/4 here. Denominator is taken with the 2 to the power denominator, so 4/4 means I can take it 4, and here it is 2, that is 2 to the power 2 is 4. 4/4 means this, I can take it as the 1/4, and when we will take it like this, then it shows here that 2 to the power TS denominator is 4. It is considered as the 4, and that is the calculated notes per beat. Here 256 linear end-to-end fits based bar measures are already taken because it is taken 1/2. In this way, MIDI ticks per note is taken as the 130.208, that is calibrated to 131. There is a 256 beats are found, and we are taking that beats per minute. 256 beats are found. So in one, if it is the 128 seconds music that I am trying to design, then how much beats per minute should I take? That is the reverse kind of calculations, for which we can take here is the 131 milliticks per note. This number of milliticks are taken per note, and that is 0.25152 microsecond per nodes, that is assigned internally, and as per our bits per minute, which is a meta event, and with that we can control the real rendering time for this music, what it is going to generate. And here we have shown that we have currently made a file for the patch number 105 that you have already seen in this Excel, that is for patch number 105, which is Sitar. Now we want to show you how the Sitar renders when we will calculate this thing with the 120 bpm, or if we calculate it with this kind of thing, that is 256 bits per bits are found in. If we want to put it 256 bits in 2 minutes, that is 120 seconds, we can take it in the 4 minutes, that is 4 minutes means 4 into 60, that is 240,000 microsecond. If we take it 240,000 microsecond, that is near around 256 bits are covered, which is 60 bits per minute in that case. So we have taken it 120 bits per minute, we have taken it 128, that is for 256 bits. For 256 bits we can take it half of this 128,000. Okay, and then we will open this file which we have generated, which has the 14 columns that I have shown in the notepad here, where we have shown in the notepad here just before opening this part, that is here in the date modified, the last file that was generated, it has a 14 number of columns here, and if we save it as a CSV, then we can see there are the 14 number of columns, and these are the column names which it is showing here, that these are the valid column names for this file. Now we will open this file, through this geometrifying trigonometry tool, and we will see that this file will convert into the MIDI file, and parallelly it will convert into a CAD file also, that is the patch demo 105 that I was showing here in the Excel. I am opening this file, and when I am opening this file, it is generating a MIDI file here, that is a MIDI file, and it is also generating a DXF file here. I will open that DXF file, and total duration is this, that as per this text box that I have written here, total nodes is 130, that is calibrated and it is shown here, and total times is shown here. Then it is generating the DXF file and the MIDI file both together. The MIDI file compilation starts, and it is arranging the data in the proper start to end ways. Now the text file is also generated, which reports the kind of data it is generated for what kind of things, so that I can do the troubleshooting on this data. And when we have done it, then we can see a CAD file is generated. We will open that CAD file and we can show you how the geometry looks like here. Here we can show you that the geometry will look like this. After doing the zoom extend, the geometry looks like this, where every region has the 1 second region, that is for the one note is here. There is a one note which is showing that 588, which means 3 is the first 3 is the track number, second one is the channel number or the instrument number, this one is the instrument number, this one is the channel number. 3 are the cases where the track number, channel number, then the instrument patch number, and 88 is the velocity. We have taken 88 as the velocity here, so the velocity is a mild velocity taken here, and note descriptions are coming in the lyrics, which is embedded into the MIDI file, where in the lyrics you can see these informations are there, which are like these, and none are written because these frequencies are not having any note number assigned. That in the Excel file we could see that in the note number there was a none was written. These are coming here, but after some time, after the cases when the real note numbers are found, then we can see that here it will write the real note numbers here, that is the A4, the concert patch 69, and it has a name, and for every note number, that is B4 71, and the hertz, the frequency in the hertz is also written, that is the 523.25, C5 72, that is the note number 72, which has a frequency 523.25. and when this one will play, it has generated a MIDI file also here. You can see a MIDI file is also generated, which is having the same name, 120 TPQN 960 1/4 2 tapes 130, that is there. I showed you in that window. Now I want to show you how it renders when we open it with Audacity and we want to play it, such that you can listen the notes, how it feels like when we open this, and how it feels like when we play it. Let's listen how the sitar gives us the effect for the different note numbers. Here you can see the sitar effect. One second per note. All notes don't behave properly for all instruments. That we have to understand. We have not added proper pitch bends here. This is the effect of sitar for different notes. It's a linear map. That means when we are going rightwards, our note numbers are also increasing linearly. These are the effects of sitar at the higher notes. This is the calibrating part. So I think you could now understand how sitar feels when we play it linearly, and how can we compose this kind of linearized musics by writing the notepad data or writing these kind of Excel files, and using the geometrifying trigonometry simulators. We can generate this kind of musics very easily, and we will show you 128 instruments with the 128 notes for every instruments. After that, your ear will get understanding that what kind of music we should choose to calibrate them, for how long we should play those things one after another, such that we can get a sequential effects, and we can compose music with CAD. And how can we compose musics with the Excel? There is a calculations, and with the music theory and with the different kind of instruments and the trigonometric behaviors, we can think about the new kind of geometries, and these kind of rearrangements of the geometries. All of these geometries can have the music and musical arrangements, and if we define what kind of geometry can choose what kind of instruments for what kind of notes at what sequence, then we can easily generate the music. We want to show you the different kind of musical arrangements that we can generate from the trigonometry problems. Those we will come one after another with this series. There is the geometry of music through geometrifying trigonometry. Thank you.